Hey everyone, so I wanted to make a video on solving systems of linear equations in two variables. So I'll go ahead and do that video here, and then I'm gonna, in a minute, make another video on linear inequalities in two variables, okay? So let's go to the whiteboard. Okay, so I am on my tablet, which is always a little bit awkward, but it's the best I can do because I don't have a touchscreen laptop, all right? So let's go ahead and look at systems of equations in two variables. So this is a 7.3 material. Actually, I think I want to use black ink. Okay, so this is 7.3 systems of linear equations in two variables. All right, so first of all, a system is two equations that we solve simultaneously. And here's the idea that we need to really wrap our head around. When you have a linear equation in two variables, you have to be very mindful of what the solution to a linear equation in two variables is. Well, the solutions to a linear equation in two variables would be all of the ordered pairs that satisfy the equation. Those are the ordered pairs that then end up creating the graph of that equation or that line. Okay, so if we have two equations that we want to solve simultaneously, we're looking for the single ordered pair that satisfies both equations. This ends up being the point of intersection. Okay, so the solution is the ordered pair that represents the point of intersection. So that represents the point where the two graphs intersect. Whoops, I forgot to see. So let's say we had Cartesian plane. And then on this Cartesian plane, we had two lines. Let's say we had this line here. And then we had maybe this line here. What we would be looking for is this point right here. This point where the two lines intersect, this would be the solution to the system. Okay, so again, we're looking for the single ordered pair that satisfies both equations. This happens to be the point of intersection. Okay, so keep all of that in mind. What I want to do first is I want to show you how to check to see if a solution or to see if an ordered pair is the solution to a system. Okay, so first example here, I would say is the ordered pair, let's use -4, 3, the solution to the system x plus 2y equals 2, x minus 2y equals 6. Okay, so what we're doing here is we have a system of equations. You usually use a really large curly bracket or curly brace, and then you just wrap it kind of around the left side of two equations that says these two equations go together. We're treating them as a single system. And if you're checking a solution, what you want to do is you want to take this ordered pair, -4, 3. You want to plug in the x and y coordinate into each equation individually. And if it satisfies both equations, you can then say it's the solution to the system. So let's look at the first equation. We have x plus 2y is 2. All right. Anywhere I see an x, I want to replace it with a -4. Anywhere I see a 2, or anywhere I see a 2, anywhere I see a y, I want to replace it with a 3. Okay, so x, which is -4, plus 2y, which is 3, we want to see if that equals 2. So I get -4 plus 6 on the left. And does -4 plus 6 equal 2? Absolutely. So we can say that this ordered pair is one of the ordered pairs on the graph of x plus 2y equals 2. So it satisfies the first equation, but for this to be the solution to the system, the ordered pair has to satisfy both equations. So next we have x minus 2y. We want to see if that equals 6. So x is -4 plus 2, whoops, that should be a minus right here. sorry. So we have x minus 2y equals 6. So I've got -4 for x, and then I want to subtract 2y, where y is 3, and I want to know, does that equal 6? Well, I've got -4 minus 6. Does -4 minus 6 equal 6? Well, no, -4 minus 6 is -10. That does not equal 6. So it does not satisfy the second equation. This is not the solution. Okay, so this ordered pair, we would say not the solution. We would have to get a true statement for both of the equations for this to be the solution. Okay, so make sure you understand that, because that's going to give you the power to check all of your answers. So once you solve a system of equations, you can take the ordered pair that you find to be the system, plug it into both equations individually. If you get a true statement, you know that that ordered pair really is the solution. In this case, the ordered pair only satisfied one of the two equations, so it's not the solution. All right, now there are 3 ways to solve systems in this class. So the first way to solve systems would be graphing. We can literally just graph the two equations and then indicate what the point of intersection would be. I do want to give you a really strong word of caution here. I'm not going to be using graph paper. I'm just going to be freehand drawing these graphs. So anytime you draw a graph freehand, it's not super precise. It's not super accurate. So it's really difficult to see for sure 100% what the solution is going to be. If you're going to solve a system of equations by graphing, your best bet is to do this on graph paper, but even better, use some kind of a graphing utility like the Desmos website or a graphing calculator, okay? So keep in mind as I go through these next 2 examples, this is going to be a situation where it's not going to be super accurate because I'm freehand drawing these, but we're going to do our best, okay? So you graph the 2 equations on the same Cartesian plane, and then you look to see if you can find the point where the 2 graphs cross. So let's look at the system. Y is equal to x plus 1, and y is equal to 3x minus 1. So here's what I'm going to do. I'm going to use the slope-intercept form for graphing. This is something that we discussed in 7.2, okay? For the slope-intercept form of graphing, we want to make note of what the y-intercept and the slope are for both lines. So for the first line, I'm going to end up graphing it in red. My slope is 1. And remember, when you're graphing, you want your slope to look like a fraction. So I'm just going to write it as 1 over 1. And then my y-intercept is 1. Remember, the constant is the y-intercept and the coefficient of x. That's your slope, okay? Now for the second equation, I'm going to graph it in blue. So for the second equation, my slope is 3. Remember, we want it to be a fraction, so I'm going to write it 3 over 1. Remember, coefficient of x is your slope. And then my y-intercept is -1, okay? So remember, this is the part where we have to be really careful if we're graphing these by hand, okay? So we're going to draw a single Cartesian plane. Okay, and then again in red, I'm going to graph the first line, and blue, I'm going to graph the second line. So for the first line, my y-intercept is 1. And then from there, I want to apply my slope. Now my slope is 1 over 1. So +1 over +1 tells me to go up 1 to the right 1. I could also, instead of going up and to the right, I could go down and to the left. Those 3 points are on the same line. So I go ahead and I connect and add those arrows. Now for the second equation, my y-intercept is -1. And then my slope is 3 over 1. So +3 over +1 tells me to go up 3 to the right 1. Or instead, I could go down 3 to the left 1. So now I've got these 3 points that are, mostly on the same line. Again, if we had graph paper, this would be perfect. All right, so we want to know, well, where do these points intersect? Well, they intersect right here. And that is the ordered pair 1, 2. Now, I can't show you on my tablet how to do this on the calculator, but just know that if you ever were in a situation where in your homework or on a quiz, a lab, a test, and you had to graph a system of equations by graphing, you would want to graph it, but always double check it with some kind of a graphing utility, okay? Because when we graph by hand, we can be off just a little bit and it can throw off our solution, all right? But that's the method for solving systems where you just graph. Let's look at one more example of this. So for the next example, let's say that we have 2x plus 3y equals 6, and then 2x plus y equals -2. Now, what I want you to notice here is for the second example, our equations are not in slope-intercept form, they're in standard form. So what I want to do is I want to take both of these equations and I want to go ahead and solve them for y. This is twofold. One, if I'm going to solve them for y, it makes graphing them really, really easy because I can just use the slope and the y-intercept to graph really quick, okay? Now, if I were to put this into a calculator or into Desmos, I would want them to be in slope-intercept form anyway. So I say just get in the habit of when you're graphing a line, slope-intercept form. It's going to be your best bet, okay? So for the first equation, I have 2x plus 3y equals 6. I want to solve it for y, so I'm going to subtract 2x. That's going to give me 3y equals -2x plus 6. I then divide everything individually by 3. So I am left with y equals -2/3 x plus 2. And again, I'm going to graph these red and blue. So for this first equation, my slope is -2/3. My y-intercept is 2. Okay? Now for the second equation, I've got 2x plus y equals -2. Here I would go ahead and subtract the 2x from each side, and I am left with y equals -2x minus 2. All right, and then we'll graph this one in blue. For the second equation, m is -2, and I'm going to go ahead and write it as a fraction, -2/1, and then the y-intercept is -2. All right, so first, again, when you have a system of equations, your best bet is to go ahead and put them in slope-intercept form, because then once you're done graphing by hand, they're already in the format where you could easily type them into your graphing calculator. All right, so let's draw a Cartesian plane. Again, I'm freehand drawing this. It's not going to be perfect, so squint and pretend. Okay, so the first equation I'm going to graph in red. My y-intercept is 2. And then my slope is -2/3. So that tells me to go down and to the right. So I'm going to go down 2 and then to the right 3. But I could also, instead of going down 2, I could go up 2. But if I did that, I would have to go to the left 3. Either way, you can see we've got these 3 points on a line. We're going to go ahead and connect with a line. Don't forget the arrows. And there's your first equation. Okay. Now for the second equation, my y-intercept is -2. My slope is -2, 1. So I'm going to go down 2 to the right 1. I could also, instead of going down 2 and to the right 1, I could go up 2, but then I would have to go to the left 1. So I've got these 3 points on a line. Graph. Pretend this is really, really perfect. Okay. And we want to figure out what this point of intersection is right here. Now, this graph, I can already tell you, is a lot messier than the first graph, but it looks like our solution is -3, 4. All right, now I can show you over here in just a second. We can look and check. Okay, so this is really important when you're graphing. Either check your answer just algebraically, like by hand, like we did on the previous screen, or you do really need to check your solution on a graphing utility, because you can see this graph that I drew freehand, it's a little sloppy. So I want to test this solution here. I want to check -3, 4 into both equations and see if it works. So for the first equation, 2x plus 3y is 6. I take 2 times x, which we think is -3, plus 4 times, plus 3 times 4. So I'm going to do plus 3y, where y is 4. We want to see if it equals 6. Well, 2 times -3 is -6. 3 times 4 is 12. -6 plus 12 is 6. 6 equals 6. Whoops, I put doesn't equal. It does equal. So the first equation is good. Now we need to check the second equation to make sure the point -3, 4 also works for the second equation. So I get 2 times 3, or 2 times -3 rather, plus y, which is 4. We want to see if that equals -2. So let's see, 2 times -3 is -6. And we need to see if -6 plus 4 equals -2. It does. So we would say that the solution really truly is -3, 4, because this ordered pair right here satisfied both of these equations right here. So hopefully this example, the second example that we're looking at now, hopefully this kind of proves to you that the graphing method for solving a system of equations does work, but it has its flaws, and you really do need some kind of a graphing utility to make sure you're getting the very accurate solution. Because this one I had to eyeball it, and I kind of had a sneaking suspicion my red line was a little off. So anyway, there you have it. So for me, graphing, great, amazing. It's very visual, but definitely use a computer or a calculator for this one. All right. Whoa. Let's see. All right. So next up, sorry about that. I ended up hitting something on my tablet. So next up, I want to show you method 2. And method 2 is an algebraic on paper kind of method. It's the substitution method. All right. So we have 3 methods for solving systems of equations. The first one is graphing. The second one is substitution. And I'm going to go ahead and just write down the steps really quickly for how to do this. I don't expect it to make sense until you see it out on paper. So the first thing you want to do is solve one equation for one variable. Sometimes this is already done for you. You'll have an equation where one equation's already solved for a variable. But if not, you need to take one equation, solve it for one variable. You then plug the result from step 1 into the other equation. And you want to solve. What this does is when you solve the first equation for one variable and plug that value into the second equation, it creates an equation that just has one type of variable, and we can solve it like we would have back in chapter 6. So then you take the result from step 3. So we plug result from step 3 into either original equation. And again, you would solve. And then the final step is super important. And this is something where my students get really annoyed with me. They're like, I solved it right, but I didn't have my answer in the right format. If your answer is not in the right format, your answer is not correct. So the big step here is write your answer as an ordered pair. All right. So let's look at an example. So first example is the system y equals 3x minus 7, and then 5x minus 2y equals 8. So what I hope you notice is the first equation has already been solved for y. So what I'm going to do is I'm going to take this value for y, 3x minus 7, and I'm going to plug it into the other equation for y. So what happens then is I get 5x minus 2y, but we're going to say y is 3x minus 7, and then that equals 8. So what I've done by having the first equation solved for y and taking its value and plugging it into the second equation no longer has 2 types of variables. It just has x's. This is something I can solve like what we did back in chapter 6. So to solve this, I would distribute my 2. So -2 times 3x is -6x. -2 times -7 is +14. That all equals 8. So then I want to go ahead and simplify the left-hand side. 5x minus 6x is -1x. So I get -1x plus 14 equals 8. And then finally, what I want to do, well, not finally, I've still got 2 steps, but the next step I would want to do is I need to get the -x alone. And to do that, I want to move the 14. So I get -x equals, well, -14 and 8, those simplify to be -6. The 14s on the left cancel. The issue here is I'm not done if I have a -x. I want a positive x. So I would divide both sides of this by -1, and we get that x is equal to 6. Okay, well, that's great. I've got half of an ordered pair. I'm currently on step 3 right here, but I need to figure out the other half of the ordered pair. So I have the x coordinate. Now I need to find the y coordinate. So what I do is I take this value for x, and I go back and I plug it into either of those original equations in the system. So I'm just going to use the first equation. I get y equals 3x, but x is 6, minus 7. So y equals 3x, that's 18, minus 7. So y equals 11. So now I have my x coordinate, I have my y coordinate, but if you go back to what we did in 7.2, x equals 6, that's a vertical line. Y equals 11, that's a horizontal line. We cannot leave our answer in this format because this format does not represent the solution to a system. Instead, we want to write our answer as an ordered pair. So the solution is the ordered pair 6, 11. And there you have it. That's why step 6 in this process is so important. All right, let's do one more like this. So for the next example, we have, let's look at 3x plus 2y equals -1. And then x minus y equals 3. Let me get some Diet Coke. Hold on. Okay. So what's different about this example compared to the first example is in the first example, step 1 over here was already done for us. For the second example, we don't have one of the equations already solved for y. So here's what I want you to really wrap your head around. You need to take one of these 2 equations and you need to solve it for one of the 2 variables. It literally does not matter which equation or which variable you choose. However, it is always best to look for an equation that has a coefficient of either 1 or -1 for one of the variables. So if I look at this second equation, the second equation is going to be way easier to work with than the first equation because the first equation would give us a bunch of fractions if we solved for either the x or the y. So I'm going to solve the second equation for x. Okay, so if I take x minus y equals 3 and I solve for x, I would add y to both sides, and that gives me x equals y plus 3. So I'm going to take this value for x, and I'm going to plug it into the other equation. So I'm going to plug it into the first equation for x. Okay, so let me show you what that looks like. So we get the first equation is 3x, but x is now y plus 3. And then the rest of the equation is plus 2y equals -1. So I now have an equation in one variable that I can solve like we did back in chapter 6. So I get 3y plus 9 plus 2y equals -1. I want to simplify a little bit here. So I look at my 3y and my 2y, that becomes 5y plus 9 is equal to -1. I want to get the 5 y's alone, so I would need to subtract 9 from both sides. 9's cancel. That gives me 5y equals -10. Divide both sides of the equation by 5. 5's on the left cancel to become 1. 1 times y is y. And then -10 divided by 5 is -2. All right, so that's my y coordinate. I now need an x coordinate. So I'm going to plug y equals -2 into one of the first equations, one of those original equations for the system. So I'm going to use the x minus y equals 3. So I get x minus y, but y is -2. That equals 3. Now remind yourself what happens when you subtract a negative. So mathematically in arithmetic, when we subtract a negative, it becomes addition. So this is really x plus 2 is 3. I then want to get x alone, so I subtract 2. 2's cancel, and I get x equals 1. So there's the x coordinate, but remember, x equals 1 is a vertical line, y equals -2 is a horizontal line. We need an ordered pair solution. Remember, the x and the y here, they're actually coordinates in an ordered pair. So we would say the solution is the 0.1, -2. And there you have it. That is the substitution method for solving systems of equations. Okay, so that's method 1, graphing, method 2, substitution. Let's look at method 3. Okay, so method 3 has 2 names. You will see it called the addition method or the elimination method, and both names make complete sense. I've seen them both in books. It just depends on the book. I grew up calling it the addition method, but elimination is great too. All right, so just like before, I'm going to explain what we need to do, and then we'll do it in a couple of examples. So step 1, put the equations in standard form. This is important. So remember, standard form is ax plus by equals c. Okay? And then step 2, it depends on the system. Sometimes you don't have to do step 2 at all. Sometimes you do step 2 to one equation. Sometimes you do step 2 to both equations. It varies greatly, but you want to multiply the equations by non-zero constants in such a way that the coefficients on one variable are opposites. Okay, so here's the general premise behind the addition/elimination method. Our goal is to add the 2 equations and have one variable get completely eliminated. The only way that can happen is if the coefficients on one of the variables are opposites. That way, when you add, anytime you add opposites, the sum is 0. So we have to kind of manipulate this. We have to force this to happen. And the way we do it is we multiply one or both equations by non-zero constants, forcing the coefficients on one variable to be opposites. So then after you do that, you add the 2 equations together. So add the equations and solve. Once you do that, you have the value for one of the 2 variables. You then plug the result from step 3 back into either original equation you want to solve. That will give you the value for the second variable. And then number 6, remember, this is the one that you all get really bent out of shape about. You're like, oh, she's so mean. She's so nitpicky. If your answer is not in the form of an ordered pair, it's not the answer. Remember, the solutions to systems of equations are ordered pairs. Your final answer needs to look like an ordered pair. So write the solution as an ordered pair. All right, now let's look at 2 examples. Which one do I want to do? Let's do this one first. So for the first example, let's say that we have 4x plus 5y equals 3. And then we have 2x. Let me make that look better. That looks kind of stupid. So we have 2x minus 3y is 7. Okay? So here's the deal. Remember, we're trying to add these 2 equations. If I were to add the 2 equations together, I would get 6x plus 2y equals 10. that doesn't do a darn thing for me, okay? Because the whole idea is we add the two equations and we force one of the variables to disappear. The only way that can happen is if one of the variables has opposite coefficients. So let's look at the x. I notice if I look at just the coefficients on the x's, I have 4 and 2. Well, 2 goes into 4 evenly. So I could really easily manipulate the second equation so that the coefficient on that x was, let's say, -4. Okay, and then if I can get the second equation to have a coefficient on x of -4, when I add the two equations, the x's would eliminate. Okay, hold on, something's happening with my computer. There we go. Okay, so that's exactly what I'm going to do. I'm going to take the second equation and I'm going to multiply the entire thing by -2. Okay, remember, if I multiply -2 times 2x, that's going to give me that -4 that I want. So let me rewrite the entire system. So my first equation, nothing happens to it. I just get 4x plus 5y equals 3. For my second equation, I'm going to multiply everything by -2. So -2 times 2x is -4x. -2 times -3y is plus 6y. And then -2 times 7 is -14. Now look what happens when we add these two equations. All right, when we add the two equations, 4x minus 4x is 0. So we just get 0 there. And then 5y plus 6y is 11y. And then 3 minus 14 is -11. All right, so 0 plus 11y is just 11y. So I get 11y equals -11. This is super easy to solve for now. I would just divide both sides by 11. The 11s on the left cancel. 11 divided by 11 is 1. 1 times y is y. And then -11 divided by 11 is -1. So we now have a y coordinate, but we also need an x coordinate. So what I want to do is I want to take y equals -1, and I want to plug it into either of the original equations. So let's say we use the first equation. So I get 4x plus 5y, but y we're saying is -1. So let's see, that's going to give me 4x minus 5 equals 3. 5 times -1 is -5. I want to get the 4x alone. The way I would do that is I would add 5. So I get 4x equals 8. The 5's on the left cancel. I divide by 2, and I get that x is equal, whoops, I just made a liar out of myself. I don't divide by 2, I divide by 4, and I get x equals 2. The 4's on the left cancel, they become 1. 1 times x is x, and then 8 divided by 4 is 2. So I've got my x coordinate. But don't forget step 6. Remember, y equals -1 is a horizontal line, x equals 2 is a vertical line. So writing them by themselves like that look like you have equations for horizontal and vertical lines. We need our solution to be an ordered pair. So the solution here is 2, -1. And there you have it. All right. So I think these are kind of fun. Hopefully you don't think they're totally miserable. But let's go ahead and look at another example where we solve using the addition or the elimination method. So first things first, let's get a new example. I have 3x equals 2 minus 4y. And then I have 5y equals -1 minus 2x. Okay. Now, if we go back to the steps here, we can see that step 1 of the method for addition or elimination, step 1 is put the equations in standard form. Equations are in standard form when you have the x term plus or minus the y term equaling the constant. So our actual system, for the first equation, I want to add the 4y back on both sides. So when I add the 4y over here, so like right here, I've got plus 4y, and I'm going to go over here and get plus 4y. That's going to give me 3x plus 4y equals 2. Now for the second equation, what I need to do is add 2x to both sides. When I do that, I get 2x plus 5y equals -1. So remember, the goal here is to add the two equations and have one variable completely eliminate. If I were to add the two equations over here on the far right, I would get 3x plus 2x is 5x. 4y plus 5y is 9y. 2 plus -1 is 1. Nothing eliminates there. So we need to manipulate one of the two one or both equations so that the coefficient on one of the two variables become opposites. So let's say that we want to get rid of the y's this time. Okay, so if I look at the y's, I've got a coefficient of 4 and a coefficient of 5. I want to find the smallest number that 4 and 5 would divide into evenly. So in this case, the smallest number that 4 and 5 would divide into evenly would be 20. Okay, so I'm going to try to force the coefficients on y to be 20 and -20. So let's say for the first equation, we would have to multiply it by at least 5. So I'm going to multiply the whole first equation by 5. That's going to make my 4y become 20y. So then that means my second equation, the coefficient on y would have to be -20. So to get a -20 on the second equation, I would have to multiply everything by -4. So let's see what that looks like. So I'm going to come down here and we're going to rewrite the entire system. So for the first equation, I get 3x times 5, which is 15x, 4y times 5, which is 20y, and then 2 times 5, which is 10. The second equation, I'm going to multiply everything by -4. So 2x times -4 is -8x. -4 times 5y is -20y. And then -4 times -1 is 4. Now, if I add these two equations up, what happens? Well, I would just add everything vertically, column by column. So 15x minus 8x, that gives me 7x. And then what happens to the y's? Well, we forced the coefficients on the y's to be opposites. I now have 20 minus 20, which is 0. So this becomes 7x plus 0 equals 14. Well, 7x plus 0 is just 7x. So I get 7x equals 14. Divide both sides by 7, and we get that x is equal to 2. So we've got the x coordinate of our ordered pair, but we also need the y coordinate. So let's plug x equals -2 into either of the original equations, does not matter which. Let's say we choose the second equation. So I've got 5y equals -1 minus 2 times x, which is +2. Okay. So I get 5y equals -1, and then -2 times 2 is -4. So that gives me 5y equals -5. Divide both sides by 5. On the left, the 5's cancel, they become 1. 1 times y is y. And then -5 divided by 5 is -1. So now I have my y coordinate. Remember, individually, x equals 2 and y equals -1. They just look like horizontal and vertical lines. We have to write our solution as the ordered pair 2, -1. It is coincidental that we got the same solution in these two examples, okay? It was just a fluke of which problems I chose, all right? So there we have it. Let's go back and kind of review really quickly. So we have systems of linear equations in two variables. It's basically two equations that we're solving simultaneously. What we're really looking for in the solution is we're looking for the point where the two lines intersect, because that's going to be the ordered pair that satisfies both equations. We then looked at how to look at an ordered pair and see if it's the solution to a system. You take the ordered pair, you plug in the x and the y coordinate into both equations. If the ordered pair satisfies both equations, that means you get a true statement when you plug those coordinates in. Then you have the solution. If the ordered pair doesn't satisfy both equations, you would say that ordered pair is not the solution. We then looked at the first method for solving systems. This was graphing. You quite literally just graph the two lines and figure out what point they intersect at. The issue with this is doing it by hand. So the first example that we did, it was a much neater graph. It was pretty clear that the solution was 1, 2. But on the second graph, it was just a little messier, and the ordered pair solution wasn't quite as obvious. So the only issue with the method 1 for solving systems, which is graphing, is you really do want to check your solution on some kind of graphing utility. So either a graphing calculator or like the Desmos website, okay? Second method for solving systems was substitution. So this is where you solve one equation for one variable. You then take that result and you plug it into the opposite equation for that variable. You solve, and then you go from there to find the other coordinate. And then method 3 for solving systems was the addition or elimination method. This one is probably the hardest one to understand at first, but once you get the hang of it, it's really fun to do. And I think it's a little bit easier once you get the hang of what you're doing. But you multiply one or both of your equations by a non-zero constant. This is the whole purpose of this, is to force the coefficients of one of the variables to be opposites. You then add the two equations, one variable cancels, and you go from there to find your two coordinates. Okay, so next up, what we want to do is we want to look at special types of systems. So there are two types of systems that when you solve them, something happens. The first system occurs where the two equations are parallel lines. Now, parallel lines never intersect. So if you have two equations that are parallel lines, you're going to get no solution. Okay, and so I'll show you what that looks like when we solve these using the substitution and elimination method. The second issue comes up where the equations graph the same line. So what happens here is you have two equations that on the surface look different, but once you really get down to the heart of the two equations, they actually graph the exact same line. And so if you're graphing one line and then the next line gets graphed exactly over top the first line, those two lines intersect, they intersect everywhere. So here we would say that you have infinitely many solutions. So basically every single ordered pair that satisfies one equation will also satisfy the other equation. So you've got oodles and oodles of solutions. The way we write the answer is a little weird, but I'll show you. All right, so let's look at two examples now. So the first example is x plus 2y equals 4 and 3x plus 6y equals 13. So for this one, let's go ahead and do the addition method, like what we just did on the previous slide. So looking at this, I see that I have x and then 3x. So the coefficients on x would be 1 and 3. If I can multiply the first equation by -3, I'll then have opposite coefficients on x. So let's look at that. So we're going to just rewrite the whole system. So the first equation, everything gets multiplied by -3. So -3 times x is -3x. -3 times 2y is -6y. And then -3 times 4 is -12. The second equation, we don't have to do anything with it, so we'll just write it down. And if you look closely, now when we go to add the two equations, the x's cancel, but the y's also cancel. All right. So then the x's cancel to become 0, the y's cancel to become 0, and then -12 plus 13 is just 1. So I get 0 equals 1, but that's not true. That's false. This indicates a system of parallel lines, and there is no solution. So you can write out no solution, or you can write the 0 with the dash through it. Either one is fine by me. All right, but just know at the end of the day, if the variables cancel when you're solving a system and you're left with a false statement, that tells you that there's no solution. All right, so let's look at the next system. Let's say that we have y equals 4x minus 4. And then we have 8x minus 2y equals 8. Well, this one is kind of set up beautifully to do the substitution method because the first equation is solved for y. So I'm going to take this value for y and I'm going to plug it into the second equation for y. So that gives me 8x minus 2 times y, but y is going to be 4x minus 4. And that all equals 8. So then I distribute and solve, I get 8x minus 8x plus 8 equals 8. Well, if I look on the left-hand side, 8x minus 8x is just 0x when I combine like terms. So I get 0 plus 8 equals 8. Well, 0 plus 8 is 8. So 8 equals 8. This is true. So this indicates two equations, same line. We have infinitely many solutions. Now, back in chapter 6, we had a situation similar to this. We had those equations, remember they were called identities, and the situation with an identity was every real number worked. So back in chapter 6, our solution to an equation that was an identity, we would say that the solution was all real numbers. Well, that just does not work here because our solutions are not just real numbers. Our solutions are ordered pairs. So how do we write the solution? Well, it's a little wacky, but you start with curly brace and then you write just a generic ordered pair, x comma y, and then you put a vertical line. This is set notation. So what this tells the reader is it says we're looking for ordered pairs, and then that vertical line just means such that. Sorry about that. So we're going to say we're looking for ordered pairs such that, and then we have to lay out the condition for the ordered pairs. And the way we do that is we just rewrite one of those two equations. So I like the equation to be in slope-intercept form. So I'm just going to go ahead and use the first equation, y equals 4x minus 4. Now, because these two equations really truly graph the same line, all solutions for y equals 4x minus 4 are also solutions for 8x minus 2y equals 8. So this notation is kind of wacky. It's called set notation. Again, you start curly brackets. You lay out the type of answer you're dealing with. We're looking at ordered pairs. So you write out a generic ordered pair, vertical line, such that, and then just lay out one of the two equations. And that's it. So that's how you solve systems of equations. You've got the graphing method. You've got the substitution method. You've got the addition method. Hold on one second. I have to send a really important text. All right. Anyway, so you've got the graphing method, the substitution method, the addition/elimination method, and now you've seen the special types of systems, the one where you have parallel lines that never intersect, they have no solution. This occurs, well, you'll know this is occurring when you solve the system and not one, but both variables cancel out and you're left with a false statement. Then the second type of situation that can come up is you have two equations that graph the exact same line. In that case, all of the variables cancel, but you'll be left with a true statement. And just be really careful with the notation there. All right. Now, what I want to do for the remainder of the video, and I know this one has gotten kind of long, I want to look at two types of word problems. Okay. So one type of word problem is called break even. And we looked at break even problems back in chapter 6 when we were doing word problems in chapter 6. But here, these are going to be a little different because we're going to look at revenue, cost, and profit. Okay, so there's a question in your book that's similar to this, and I'm just going to kind of write it out here. So a company makes shoes. I think in the problem, it's very specifically running shoes, but I just kind of condensed it a little bit. So a company makes shoes and has costs. We'll call it fixed cost, has fixed costs of $300,000. So imagine a company, they're going to have costs that just occur over and over. So it might be a rent or a mortgage on a building. This could be utilities. So to run a business, you have to have electricity. You might have to have water. You're going to definitely have payroll. Okay. And then in addition to that, you're going to have costs associated specifically with the product. So we have fixed costs of $300,000. Those are things that occur just every month, no matter what. And then additionally, too bad I can't spell, additionally, each pair of shoes costs $30 to make. So think of the cost for the shoes as like the materials that you would have to buy. So you have to buy some kind of material for the soles of the shoe, some kind of material for the actual shoe itself, material for the holes that make up the laces, material for the laces, okay? So those costs would be $30 per pair of shoes. The shoes are then sold for $80. Okay, and what we want to do here is we want to find three really important things, and then we'll kind of play around with a fourth thing. The first thing we want to do is write a function that represents cost. So remember, we talked about function notation back in 7.1. So function notation is back. So first of all, let me actually, even before we get to this A, we're going to need to assign a variable. We're going to let X equal the number of shoes that are produced and then sold. Okay. So for part A, we want to find the cost function. And we're going to call it C of X. So the cost to produce shoes, well, we have those flat fixed rate or fixed costs of 300,000. Remember, that could be the cost for the building. It could be cost for machinery. It could be utilities, electricity, water, whatever. It's also going to be payroll. But then in addition to that, we have a cost of $30 per pair of shoes. And remember, those costs would be like the materials that you have to purchase that make each pair of shoes. Okay, so that's our cost function, fixed cost plus the cost per pair of shoes. The second thing we have to look at is revenue. So we want to find the revenue function. And the revenue function, we'll call it R of X. Now, revenue is all of the money you bring in. So for every single pair of shoes you sell, you're bringing in a certain amount of money. So the revenue function is just going to be the cost, or not the cost, but the price we sell the shoes for. So it's going to be 80X. Now, step C is the tricky one. It says find the break-even point. So here's what you need to know about break even. Break even occurs when revenue equals cost. So if your money going in and out is the same, you break even. You're not making money, but you're also not losing money. And this is very important for people that are producing some kind of product. They need to know exactly how much of this product they would need to sell so that their costs equal their revenue. The goal is then to sell more than that, but definitely not less than that. So if we're going to find the break even, this occurs when the revenue is equal to the cost. Okay. So if we have R of X equals C of X, that's going to be 80X equals 300,000 plus 30X. Okay. So what I would want to do is get all of my X's on one side of the equation. So I would subtract 30X from both sides. Whoa. Sorry. I would subtract 30X from both sides. That gives me 50X equals 300,000. The 30X's cancel, they just become 0. So then I would need to divide both sides by 50. And that would tell me how many pairs of shoes I would have to sell to break even. So I would then take 300,000, I would divide it by 50, and I get X equals 6,000 pairs of shoes. Now, this is great. We know that if we sell 6,000 pairs of shoes, we break even, but we want to know what break even is. We want to know what that value of money is. So that's going to tell us how much we spend each month, how much we bring in each month to where we break even, we get 0. Okay. So I then take X and I plug it into R of X or C of X, and we'll do both just for the sake of this problem. So if I take R of X, that's going to be 80 times X, which is 6,000. All right. So 80 times X of 6,000 is going to be 48, 480,000. Similarly, if I take 300,000 and add that to 30 times X, where X is 6,000, I get 300,000 plus 180,000 or 480,000. So what this tells me is if we make and sell 6,000 pairs of shoes. Cost, that's not how you spell cost. Cost and revenue are equal at 480,000. Okay. Now we also want to talk about profit. Okay. So I'm going to do profit on the next screen because I'm just out of space here. So profit is equal to revenue minus cost. Okay. So let's call profit P of X. We already called revenue R of X, and cost is C of X. So our goal is for this to be a positive value. So if we let X equal exactly 6,000, profit is 0. Okay. So let's look at this really quick. So let's put in the actual functions here. So P of X we know is going to be revenue minus cost. So that's going to be 80X minus 300,000 plus 30X. That's revenue minus cost. So the profit function would then be 80X minus 300,000 minus 30X, or 50X minus 300. Bless my heart, geez. Minus 300,000. Okay, so this is the profit function. And we literally found this by taking the revenue function, subtracting the cost function. So let's look at P of 6,000. Remember, 6,000 was the break-even point. So we want to know what our profit is if we sell exactly 6,000 pairs of shoes. Well, I would get 50 times 6,000 minus 300,000. Well, 50 times 6,000 is 300,000. So you can see the revenue is equal to the cost and profit is 0. So just for fun, let's look at a number less than 6,000 and a number greater than 6,000. Whoa, there we go. So let's look at P of 5,500. Okay. So if we have P of 5,500, that's going to be our X. So we would take 50. Remember, we're plugging it into this function right here. We would get 50 times 5,500 minus 300,000. So really quick, let's figure out what 50 times 5,500 is. So 50 times 5,500 is 270,000. Wait, 275,000. We need to subtract 300,000. And unfortunately, that puts us at negative 25,000. So if we sell 5,500 pairs of shoes, our profit is negative 25,000. So we lost money. Okay. But let's look at a number greater than 6,000. Let's say we sold 6,500 pairs of shoes. So again, we're plugging that into the profit function. We would get 50 times 6,500 minus 300,000. So let's see what 50 times 6,500 is. So 50 times 6,500 is 325,000. We then subtract 300,000. And we can see here, if we sell more than 6,000 pairs of shoes, we have made a profit. In this case, we made a profit of $25,000. Okay, so hopefully this kind of shows a little bit about how profit, cost, and revenue are related and how important that break-even point is. So if you run a company, you're producing something, you need to know what your costs are. You need to know what your revenue is. And most importantly, you need to know what your break-even point is, because your break-even point helps you figure out what your target needs to be. So once you figure out your break-even point, that means your profit is 0. Okay. We don't want a profit of 0. We want a positive profit. So we would try, in this case, if we knew our break-even point was 6,000, we would try our hardest to sell as many pairs of shoes over 6,000 as possible. The more shoes you sell over 6,000, the greater your profit is. All right. So that is solving systems of equations. There is another type of problem you could see that I will go over just really quickly here. you have to go back to what you learned in chapter 6 about direct translation. Okay, so direct translation is where we take math, we convert it, or we take words and we convert it to math. So we did a lot of word problems. We did consecutive integer problems. We did the break even problems. There was one that we did about a hot air balloon. There was another one about people meeting in a stairwell. We did just regular direct translation problems. We had one about like a board that we were cutting into 2 pieces and one piece had to be a little bit longer than the other. We did all sorts of word problems. So you need to take that idea from back in chapter 6, but now apply it to chapter 7 or section 7.3, where we're looking at systems of equations. So let's say for fun that 5 bags of chips and 9 bags of pretzels cost $16.95. If you have 10 bags of chips and 10 bags of pretzels, it costs $25.50. How much does each individual item cost? So we're dealing with systems of equations in 2 variables. So let's come up with 2 variables. Let's say C equals bags of chips. And let's let P equal bags of pretzels. We now need to come up with 2 different equations that we could then solve to figure out the cost of each individual item here. So first of all, we know if we have 5 bags of chips, that would be 5C. And additionally, 9 bags of pretzels, 9P, the total cost would be $16.95. Similarly, if we had 10C, 10 bags of chips, and 10P, 10 bags of pretzels, that would equal $25.50. We have now created a system of equations, and if we solve this system of equations, we'll get values for C and P, which would end up being the cost of a bag of chips individually and the cost of a bag of pretzels individually. So you could solve this any way you wanted to. I noticed right here that the chips in particular, the coefficients are 5 and 10. If I multiply the top equation by -2, I would get opposite coefficients on the bags of chips, and I could easily solve this using the addition method. So that's what I'm going to do. So the first equation, if I multiply everything by -2, let's see, I get -10C minus 18P equals 3390 maybe. Let me double check that so I don't make a big mistake here. Yeah, so that's going to equal -3390. So that's the first equation where we multiplied everything by -2. And then the second equation, we're going to leave it exactly as is. We're not going to do anything to it. Okay. Well, when I add the 2 equations, -10C plus 10C just becomes 0. -18P plus 10P becomes -8P. And then -3390 and 2590, that's going to be what, like 740 maybe? So I then want to subtract 2550. Whoops, 3390 minus 2550 is $8.40. I don't remember what I said. I think I said 7 something. So $8.40, but it is going to be negative because we have more negative than positive. So now I've got -8P equals -840. I need to divide both sides by -8. And I get that P is equal to $1.05. All right, so that tells me each bag of pretzels is $1.05. We're going to now use that to figure out the cost of a bag of chips. Okay, so I'm going to plug P equals 105 into, let's say, the first equation. So I get 5C plus 9P, where P is 105. and then that's going to equal 1695. Well, let's see here. 9 times 105 is going to be what, 945? Sorry, I've talked a lot this morning and I'm needing water desperately. So plus $9.45 equals 1695. I need to subtract $9.45 from both sides. That's a 45. So let's see what we get there. We get 5C equals 7.5. I divide both sides by 5, and we end up getting that each bag of chips is $1.50. So chips, $1.50 per bag, and pretzels are $1.05, and that would be your final answer. So you could have lots of questions like this one where it's just basic direct translation. You could have those questions where you're dealing with like the revenue, the cost. Let's see here. How do I get rid of this one? So you could have those equations or the questions where you're dealing with revenue, cost, and profit. Whoops. Sorry, my tablet, it's a little awkward for me to make videos on. So anyway, as far as the word problems go, you could have just the basic direct translation like the chips and the pretzels, okay? You have questions like that on your lab. You also could have the profit, revenue, and cost. So you have that. Make sure you understand the 3 methods for solving systems of equations. Graphing, you really do. This always looks so crazy. Like my tablet is so low to the ground, it's like you're looking up at my face. Anyway, so you've got the 3 methods for graphing, or for solving systems of equations. You've got graphing, which really does need to be backed up with like Desmos or a graphing calculator. You have the substitution method, you have the addition or slash elimination method, and then you have the 2 special types of systems. The one where you have no solution, that's parallel lines, or the one where you have infinitely many solutions, that occurs when you have 2 equations that graph the same line. Okay, so hopefully this video helps. If you either missed class when we covered this, or if you were struggling a little bit, here you have it. All right, good luck.